as you saw, part of figuring out the torque that an object experiences has to deal with where the center of mass of that object is, or the center of gravity of that object, where that is, so you know where to put the vector for the force of gravity. For an object that is symmetric and homogeneous, like this meter stick, then the center of mass is going to be directly in the center of the meter stick, or whatever object it is you're talking about. If you have a perfect square of material, the center of mass is going to be right smack dab in the middle of that square. Okay? So if you were to try to spin the object around, that would be where it would spin from, or where it would balance from if you were trying to balance it. Okay? Just like I can balance the meter stick by putting my finger basically at the center of it. Okay? So, if the object is uniform / homogeneous and symmetric, then it's very, very easy to find where the center of mass is. It is just at the center of the axis of symmetry and the very center of the object, therefore. Okay. So, if instead I don't have that idea, if the object is not homogeneous, say it's like some kind of battle axe, where there's much more weight up here than there is down there, then we have to look at this either experimentally to try to figure out what the center of mass would be by balancing it on a knife edge, or we have to actually calculate it. And it's easier to think about this in terms of breaking it into a number of particles. And as I was mentioning in class, that means you'd have to find a center of mass in the x direction, a center of mass in the y direction, and a center of mass in the z direction, and those would be the coordinates for the actual center of mass of your object. So, what that means is that the center of gravity in the x dimension for the x coordinate has to deal with the positions of every particle you have with this coordinate in the x dimension divided by the total mass that's around. So let me put capital M there. Okay. So this also is true for the y dimension and the z dimension. So again, what this sum means is that if you have some number of particles that make up the system or object that you're trying to figure out the center of mass for, then you would look at each individual particle that's there, and you would multiply it by its coordinate position. And then you take that and divide it by the mass that's in total. This is a weighted average, basically, taking into account all the different mass that's along each dimension. So in the idea of the battle axe, or hatchet, looks a little more like a hatchet, if you were measuring over here to have your 0 point for the origin of your xy coordinate system, then you would say, okay, this chunk of the axe handle at this position has this much mass, so I'd put that much mass times the x coordinate, and then keep on going over here, keep on going over here, continue on, and it's like, oh, this bit of mass over here is more, because it's a bit denser part, it's more of the metal than the wood, so it would have more mass in that direction, so you have to figure out that would be the weighted average part that would come into play, and then you have to do the same thing for the y direction, noting that, oh, there's more mass over here, and there's less mass down here, so center of mass is going to be somewhere up there, in the y direction. So then you would have the y coordinate for the center of mass, you have the x coordinate for the center of mass, and you'd be able to figure out what the overall coordinate is then too by putting those two things together. So if you have three particles, what's the center of mass? Let's do that as an example right now. So let's say we have our xy coordinate system set up. And let's say, let me look at my example, that we have a 2.00 kilogram mass at the origin, and we have a 5.00 kilogram mass, a distance of 0.0500 meters to the left of the origin, and then we have a mass of 4.00 kilograms 1 meter from the origin. So now we need to figure out, for this example, where's the center of mass of these three particles. Okay, so we only have mass in the x dimension, so we only need to look at that first one. So x, center of gravity, is equal to the sum of each particle at its coordinate position divided by the total mass of what's around. Okay, so that means the x center of gravity is equal to, let's look at this one first, it's equal to the 5 kilograms here times negative 0.500 meters, since our origin is right there. So that's 5.00 kilograms times negative 0.500 meters. The next one is the 2 kilogram mass, but its coordinate position is 0. So that is actually going to give us 0, since our x for that spot is 0. This part then is at 4.00 kilograms times positive 1.00 meters. I take those together and I divide by the total mass, which would be 5.00 kilograms plus 2.00 kilograms plus 4.00 kilograms. So while the 2.00 kilogram mass doesn't matter in the numerator, it does, however, matter in the denominator because we have to deal with all the massive particles that are there. So then if I work out the numbers, I end up with an answer that is 0.136 meters. So the center of mass of this system, if I wanted to balance this system, I would need to place a finger right there at 0.136 meters. And then the torques would end up being equal because the forces would work out with their distances to make it balance. That's part of the definition of what the center of gravity is. If you were to try to balance it, you'd want to do it at that point. So the sum of the torques around that position would end up being 0. So oftentimes it's helpful to actually, for a certain problem, put your center of rotation at the center of gravity, but it all depends on what system you're looking at, because it might not be as convenient to do that. Remember that we are free to move that axis of rotation wherever we want to analyze the torques. Okay, and we'll be dealing more with the application of mechanical equilibrium and the sum of the torques being 0 and the sum of the forces being 0 and the center of mass in classes to come.